Hello, I'm Yijin Chen from Computer Science Department, SUNY at Albany. Today, I will talk about our research on context-aware regression test selection. First, I will introduce the problem we want to solve and the current solutions and their limitations. Then, I will introduce our methodology, follow with empirical studies and case studies, and then end with conclusions. The problem we'd like to solve is the regression test problem. Most of our systems are continually evolving to serve users better or meet our new needs. The ongoing changes may take place in system and their supporting execution context, like a library change or API change. To make sure those changes will not introduce bugs, we need to conduct a regression test to find the regression fault, which cause previous working function to fail. We can define the regression test problem as given the program P and a modified version of program P prime, and the test suite T and T prime if test suite is modified based on the program P prime, to find the solution to have a subset of T or T prime which to test P prime, which there are several techniques. However, we only focus on regression test selection, which is a technique seek to reduce the size of test suite and focus on modification traversing test cases. The challenge for the regression testing is how to find the modification traversing test case, which can cover both code change and execution context change. There are a lot of techniques has been proposed and focused on regression testing, but some of those are focused on code change only, some of those focus on specific execution context only. Not all of those can cover both code change and execution content change. In that table, we can see the slicing, CFGS, fireware, UML, partition. Those are all code change. For the SQL-based Lambda, this is very specific for the database cannot change. For Itazi, HYRTS, they can cover code change and sort of execution content change, but they cannot detect database change and API change. So our technique called CART can cover both code change and library change, configuration file change, database change, and API changes. Our methodology uses program environments. So we use program environments to identify modification reviewing test cases, which can cover the changes in external API, configuration files, libraries, and the database. What is program environment? A program environment is a program property that holds a true value at a specific program point during the execution of the program. We can define that as a table I equals P, V, C, where P is program point, V is set of variables, and C is a relationship or condition imposed on V. Here is an example function withdraw. It takes money as input and takes away money from the balance when balance is greater than money. The post condition of the function shows the state after execution. In this case, there are three program environments. The program point is function name, class name, and function name. The keyword enter or exit indicates its pre-condition or its post-condition. And the variable money balance, and C is like the relationship or the condition. Here is an example shows how program environment correlated to the library, file, configuration files, APIs, and the database. So this is class C has two class attributes. One is a database variable, DB var, another is var var, var2. It has three functions, function 1, function 2, and function 3. Where function 1 calls library's function library underscore 1, and function 2 reads files from a file path and fetch data from an external API call. F3 uses a variable associated with a table column in the database. We have 4 test cases: TC1, TC2, TC3, TC4. We run these test cases with instrumented class C and then generate program environment transparency matrix, which called ITM, which shows on the right-hand side of the graph. ITM is to render the relationship between the program environment and the test case. So you can see the first column is program point, the second column is the variable set, and the rest shows the correlation between test case and the program environment. 1 means the test case executes as variable at specific program point. 0 means that this program environment has no relationship with this specific test case. In the ITM, it is clear to see the library, file path, API, and database info are captured in the ITM, which can be further used for the regression test selection. We learned the program environment and how it's related to the code change and the context execution change. Here is a summary about our methodology. So first, we obtain the program environment. Second step, we create an environment transparency matrix, ITM, and use ITM to find modification traversing test cases. So for the code change, we identify the changes to the program, function, variables by using def or checksum, and then use ITM to select all the modification traversing test cases that execute those modified parts. If a new test case created or test case modified, we can compare the program environment of modified test case versus original test case to find out affected program environments, and then use them to identify the modification traversing test case. For the execution context change, such as library change, so every function f in P, the program that calls the library is affected, and all the tests that execute f will be selected. For the database change, we use ORM to find the environments referring to the database changes, entities, or relationship. For the API change, a function f in program P that calls change the API is affected. All the test case that execute f will be selected. For the file change, a variable v in the program P that refers to the settings like file name, path, and that variable is affected. All the test cases execute this variable will be selected. We conducted 3 controlled environments on open source programs. They have reported regression fault and test suites to evaluate the efficiency of our approach. The first experiment was to investigate the effectiveness of our approach for the code change. The second one focused on the change in the library. The third one focused on database change. The projects we selected are all open source projects, Java application, and has well-defined test cases. Here is the result of selection on code changes. For the code change, we compare the program between versions. We compare our method with execution trace method approach, FRTS, and HYRTS approach. The result shows our method is similar as the execution trace method, but slightly better than FRTS and HYRTS. Because FRTS and HYRTS are file-based, and the execution trace is statement-based, and our method is function-based. In the second empirical study, we changed the version of the library. The project built on Maven, so simple change the POM file can upgrade or downgrade the library. Our method can find all the regression faults by selecting on average 20% of the test cases. In the third empirical study, we had some changes in the database. So our method can find all the regression faults, and by selecting on average 18% of the test cases. Above the empirical study are controlled experiments on the open source program and for the purpose of evaluating the effectiveness on single effects. Case study here demonstrate the performance of our approach on industry systems. The first one is education system, which has the backend as Java application, frontend is JavaScript, and use a relational database. The second one is biological data analysis and the visualization application. The third one is cancer repository system. We first annotate the application and ran the test case provided by the developer team to construct a diagram. Then use it to conduct a regression test session. We compare our result with execution trace and retest all approach. Here is the result of case studies. So for the case study 1, A1, A2, A3 are code change. A1, A4, and A5 had changes in execution context. So A1 is the combination of the code change and execution context change. For B1, case study 2, B1 is an API change and B2 is code change. In the case study 3, C1, C2 are code change, and C3 is database-related change and code change. In this table, the TC represents stated test case. The RF represents regression fault. From the table, we clearly see our method CARTS can select all the regression faults. ET can select regression fault and have better performance at code change. However, it fails in several cases like A4, A5, B2, C2, C3, which are execution context-related changes. Here's the summary. Our approach is safe because it can cover both code and execution context change. The study results shows that it selected all the 4 reviewing test cases in these studies. For the code change, our approach is as effective as the traditional approaches. For the changes in execution context, our approach can also select all the 4 reviewing test cases. The conclusion is, in the regression testing, our approach successfully selects all the 4 reviewing test cases caused by the changes in both execution context and the program code. For the future work, we try to apply our methodology to other new program languages, also working on the optimize the type of environment to improve the precision. Thank you.